Hello everyone, I'm Akash. In today's video, I'm going to solve a question on ring theory from NBHM 2011 exam. Question is, which of the following is or are prime ideal in the ring of continuous function over closed interval 0? We have given three different ideals and we have to determine which of these ideals are prime ideals. Before going to the solution, I like to tell you that those students who are preparing for CSIR NET, GATE, TIFR or any PhD entrance exam should also watch this video because such a types of questions are also asked in these exams. So let's begin the solution. Let's recall the definition of prime ideal first of all. Let R be a commutative ring and P be an ideal of R. Okay. Let R be a commutative ring and P be an ideal of R. Then P is a prime ideal of R if AB belongs to P implies A belongs to P or B belongs to P. This is a standard definition of prime ideal, and the condition is if AB belongs to ideal P, then this should implies A belongs to P or B belongs to P. If this condition is satisfied, then ideal P is a prime ideal of R. Okay, so let's verify whether I is a prime ideal or not. For this, let's define a function f of x which is equals to 0 if 0 less or equals to x less than 1 by 2 and x minus 1 by 2 if 1 by 2 less or equals to x less or equals to 1. Okay, let's draw the graph of this function. Okay, at x equals to 0 it is 0. Okay, at x equals to 1 by 2 it will take 1 by 2 minus 1 by 2, that is value 0, and between 0 and 1 by 2 it will take value 0. So from 0 to 1 by 2 it is a just constant function. Okay, and at x equals to 1 it will take 1 minus 1 by 2, that is 1 by 2 value. So at x equals to 1 it will take something value here 1 by 2. So its graph look like this. Okay, this is the graph of f of x. So from graph we can see that its curve, it is a continuous curve. So it is a continuous function defined on closed interval 0. Okay, now let's define another function g of x. G of x we define as here 1 by 2 minus x if 0 less or equals to x less than 1 by 2 and equals to 0 if 1 by 2 less or equals to x less or equals to 1. Now let's draw its graph. At x equals to 0 it will take value 1 by 2, something here. Okay, and at x equals to 1 by 2 it will take value 0. So its graph look like this. Okay, and after 1 by 2 it will take value 0. Okay, so its graph looks like this. Okay, this is the graph of g of x. Okay, and again we can see that its graph is a continuous curve, so it is also continuous function defined on closed interval 0. So by definition of f comma g, we see that f and g belongs to a ring of continuous function over closed interval 0. That is, they are the element of this ring. Now let's see what is the function fg. Okay, by fg I means not a function composition, I mean f of x times g of x. Okay, let us see what is this product. Okay, clearly when we multiply these two functions, that is f of x times g of x, it takes value 0 times this, that is 0 if 0 less or equals to x less than 1 by 2, and x minus 1 by 2 times 0, that is again 0 if 1 by 2 less or equals to x less or equals to 1. Okay, so fg is 0 for every x belongs to closed interval 0. Okay, that is, it is a constant function and it is a 0 function for every x belongs to closed interval 0. So it is again a continuous function and belongs to this ring. Okay, but this function also satisfies this condition, that is, so this implies fg of x equals to 0 if 1 by 2 less or equals to x less or equals to 2 by 3, because 1 by 2 and 2 by 3 are belongs to this interval, and fg satisfies this condition, fg of x equals to 0 for every x in this interval. So it must satisfy this condition in every sub interval. Okay, and this is nothing but sub interval of this interval. Okay, this is nothing but equals to close interval 1 by 2 comma 2 by 3. So fg satisfies same condition in this sub interval also. So this implies fg satisfies the condition of ideal I. So fg belongs to I. Okay, fg belongs to the ideal I. However, by definition of f and g, it is clear that f does not belongs to I and g does not belongs to I. Okay, because f of x not equals to 0 on this interval and g of x not equals to 0 on this interval. So f and g does not belongs to I, but their product fg belongs to I. So by definition of prime ideal, we see that this implies I is not a prime ideal of C of 0. Okay, so I is not a prime ideal of C of 0. So we discard it. Okay, this is not option, just I have tick cross symbol because this is not a prime ideal. Now let's verify whether J is a prime ideal or not. Now let's verify whether G is a prime ideal or not. For this, define a function f of x equals to x minus 1 by 3 and g of x equals to x minus 2 by 3. By definition of f and g, clearly they are the continuous function defined on closed interval 0, 1. So they belongs to the ring of continuous function over closed interval 0, 1. Also, by their definition, f of 1 by 3, if we substitute x equals to 1 by 3, then we get value 0. And similarly, g of 2 by 3 equals to 0. Okay. Now, consider the product of this function. Product means f of x times g of x, not the function composition. Okay. Now, consider the product of this function f of x times g of x, which is equals to x minus 1 by 3 times x minus 2 by 3. Clearly, we see that fg of 1 by 2, sorry, fg of 1 by 3 equals to 0 and fg of 2 by 3 is equals to 0. Because when I substitute x equals to 1 by 3, this term becomes 0 and 0 times this term is again 0. And when I substitute x equals to 2 by 3, this term becomes 0 and 0 times this term is again 0. So the product is 0 at 1 by 3 and 2 by 3. So by definition of J, we have Fg belongs to J because J contains all those continuous functions in over 0, 1 for which f of 1 by 3 equals to 0, f of 2 by 3 equals to 0. Here fg of 1 by 3 equals to 0 and fg of 2 by 3 is also equals to 0. So the function fg belongs to J. Okay, but by definition of f and g, F does not belongs to J and G does not belongs to J, because we need both these values 0, that is f of 1 by 3 equals to 0 and f of 2 by 3 equals to 0. Here if we substitute value x equals to 2 by 3, let's f of 2 by 3, then f of 2 by 3 is what? 2 by 3 minus 1 by 3, which is equals to 1 by 3 not equals to 0. Okay, so f of 2 by 3 not equals to 0, so f does not belongs to J. Similarly, g of 1 by 3 not equals to 0, so g does not belongs to J, but their product fg belongs to J. So by definition of prime ideal, we see that J is not a prime ideal of ring of all continuous function over closed interval 0. So J is not a prime ideal of this ring. So the only ideal which remain is K, and yes, it is a prime ideal. So let's prove it. Now let's prove that the ideal K is a prime ideal of ring of continuous function over closed interval 0, 1. For this, let's define the mapping phi from the ring of continuous function over closed interval 0, 1 to a ring of real numbers by phi maps the continuous function in this ring to a real number f of 1 over 3. Okay, phi maps the continuous function in this ring to a real number f of 1 over 3. Then we can easily prove that phi is a ring homomorphism. To see this, consider phi of f plus g, where f and g are elements of this ring. Then by definition of phi, this is equals to f plus g of 1 over 3. Okay, and by definition of addition in this ring, this is nothing but equals to f of 1 over 3 plus g of 1 over 3, and phi of fg is equals to fg of 1 over 3. Okay, and by definition of product in this ring, we have used the definition of product as f of x times g of x, not as function composition. The definition of product in this ring is like this. So by this definition of product, this is nothing but equals to f of 1 over 3 times g of 1 over 3. So phi satisfies these two properties of ring homomorphism, which is the definition of ring homomorphism. So this implies phi is a ring homomorphism. Okay. Now let us prove that the mapping phi is onto as well. That is, it is an onto map. For this, clearly for every real number R, there exists a function f of x defined by x minus 1 by 3 plus R belongs to ring of continuous function or closed interval 0, 1, such that phi of f, phi maps this function f to f of 1 over 3, and f of 1 over 3, when we substitute x equals to 1 by 3 here, we get 1 by 3 minus 1 by 3, that is 0. 0 plus r is nothing but r. So f of 1 by 3 is equals to r. So we see that for every real number, there exists a function f of x in this ring. That is, for every element in codomain, there exists an element in domain. And so this implies the mapping phi is onto map, that is surjective mapping. Okay. So up to now we have proved that phi is a onto ring homomorphism, and we will use this fact to use the fundamental theorem of ring homomorphism. So by fundamental theorem of ring homomorphism, as phi is an onto ring homomorphism from ring of continuous function or closed interval 0, 1 to R, hence the factor ring is isomorphic to ring of real number. This is by fundamental theorem of ring homomorphism. Let us write the statement of fundamental theorem of ring homomorphism. The fundamental theorem of ring homomorphism states that if phi from R to R dash is an onto ring homomorphism, then there exists an isomorphism, okay, then there exists an isomorphism psi from ring factor ring R over kernel of phi to R dash. That is, ring R over kernel of phi is isomorphic to ring R dash. This is the statement of fundamental theorem of ring homomorphism, which we have used here. So by this fundamental theorem of ring homomorphism, we have the factor ring of continuous function over closed interval 0, 1 or its kernel is isomorphic to ring of real number. Okay. Let us first determine what is kernel of phi here. Now, kernel of phi is equals to set of those elements in domain, set of elements in domain such that phi maps those elements to a identity element of codomain, zero element of codomain. And what is zero element of ring of real number? Is the real number 0. So this is nothing but equals to set of f belongs to C of closed interval 0, 1 such that f of 1 by 3 equals to 0, because definition of phi of f is f of 1 by 3. So we get this, and clearly this is nothing but the definition of ideal k. Okay, we can see that this is the definition of ideal k. So this is equals to k. So we see that kernel of phi is nothing but is equals to the ideal k. So this implies the factor ring, this factor ring is isomorphic to ring of real number. Okay. Now we will use the result. Let R be commutative ring with unity. Let R be a commutative ring with unity. Then R by M is an integral domain if and only if M is a prime ideal of R. Okay, we will use this result. Okay, we will use this result. Now, in our case, this is a ring of real numbers, and we know that ring of real number is an integral domain. So as this is an integral domain, so this must be also an integral domain, because both these rings are isomorphic. As this ring is an integral domain, so this is also an integral domain. And so by this result, the R by M is an integral domain if and only if M is a prime ideal of R. That is, if and only if K is a prime ideal of ring of continuous function over closed interval 0. So from here we get that the ideal K is a prime ideal of ring of continuous function over closed interval 0. So this is the required ideal. So the answer to this question is the ideal K is the required prime ideal of ring of continuous function or closed interval 0. Okay. In fact, we also have the result that R by M is a field if and only if M is a maximal ideal, okay, of R. Okay. So we know that ring of real number is a field also. So as both the rings are isomorphic, so this ring is also a field. So by using this result, we see that the ideal K must also be a maximal ideal of ring of continuous function over closed interval 0. So the ideal K is not only a prime ideal but also a maximal ideal of the ring of continuous function over closed interval 0, 1. Okay, this is not only a prime ideal but also a maximal ideal of this ring. Okay, now I want to give you a task. Okay, prove that this ideal K is a maximal ideal using the definition of maximal ideal, not by using this result. Okay, that is, use the definition of maximal ideal to prove that the ideal K is a maximal ideal of ring of continuous function over closed interval 0. If you have any difficulty in proving this task, then please comment on this video. I will make separate video on this task. Okay. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.